Cool. 815 bus routes. We have a list of, oh man, when I heard that now, I feel like maybe this is going to be another graph farm, and I really don't want to do three graph farms in a row, or at least not like, should add a low diversity, but I guess we'll see. We have a list of bus routes. Each route sub I is a bus route that the ith bus repeats forever. For example, if route sub 0 is equal to 157, it means the first bus travels in the sequence 157, yada, 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 forever. We start at bus stop S, initially not on a bus, and we want to go to bus stop T. Traveling by bus only, what is the least number of buses, fewest number of buses, we must take to reach our destination? Return -1 if it is not possible. Routes 1 to 7, 3, 6, 7. You want to start at 1 and you want to end at T. Output is 2. The best strategy is to take to. Okay. Now, this is maybe a fun problem. Okay, I mean, it's still graph E, but maybe not. Seems like 10 to the 6 is a million. How do I want to do this? Let's see. I mean, my first intuition is that, so there could be up to 500 things. Yeah, my first intuition is some kind of breadth first search, but let me see if I understand this actually first. Okay, so take the first street to bus stop 7, and then take the second bus to bus stop 6. Oh, huh. Okay, so actually this is only the fewest number of buses and not per time. Okay. I think the really okay. So actually, initially I thought you would actually. I mean, I know that I read the poem, but I'm bad at reading, I guess. But I actually initially thought that we would have to do minimum number of stops or something like that. Actually, but this is maybe slightly easier. Okay, so you have 500 routes, right? So which is highlighted here. So you have 500 routes, which means it seems like at most the answer is 500. So let's say if you cannot do in 500 iterations, then or whatever the answer is, then you cannot do it, right? So that kind of helps us bound things to maybe some kind of and I think the really naive thing to do is to kind of like construct a huge adjacency matrix, maybe even sparse one. Maybe that's okay. No, but that but on the so initially my thought would be to construct some kind of adjacency graph, just a graph on the sequence itself. I don't know what these numbers represent. So so in the stop itself. So for example, in this case, you could eventually do if n was smaller, you could do some transitive kosher calculation or something like that, and then that's really easy, right? And then you just kind of do the shortest path with that. But it seems like that's not the case yet. But this is still a shortest path problem, and I think given okay. I mean, it's definitely a shortest path problem. So I'm just trying to think. Okay, so you have each route, and the question is how many routes. So the first question I would ask myself is kind of for each route, which other routes does it intersect or stop at the same stop or something like that, and that depends on kind of the length of these two. Because well, they're the same length, then you just do a for loop for each of them. I think there's and I'm trying to think if there's a clever way to do this based on the greatest common denominator or greatest common factor, or no, least common denominator. No, but basically the GCD. But for example, if the weight is 3 and 3, then you just do 3 loops. And because n is 500, approximately the biggest number that you can do is 500 square, which is 25,000, I think. 200, no, yeah, 25,000. But yeah, so that should be maybe okay. Yeah, okay. So this is a little bit hacky. I mean, there's definitely a math-y solutions for this. Uh, but because basically, if two number, I kind of skipped ahead a little bit in my jump thought process, but basically, well, if two numbers are not relatively prime to each other, then essentially, like, okay, let me I forget what the formula is. It's been a while, but basically, let's say you have two relatively prime numbers to each other. Let's say 499 and 500, right? They have no common they have no common factors because is 499 prime? I actually don't know, but 499 does not share a factor with 500. So in that case, you do loops up to 499 times 500 times, and then that's kind of your upper bound on your complexity because there's a lot of number theory that I don't know. I mean, it's not a lot of number theory. It's some basic number theory. I just don't know how much to explain. And definitely please ask questions if I'm going a little too fast or making assumptions that you don't think I. Yeah. So yeah, it's going to be some sort of BFS, but first you have to construct a graph to do the BFS, and two routes intersect if so the two routes intersect if, for example, you have 1, 2, 7. I definitely jumped ahead way too much. Sorry about that. Let me explain this a little bit better. So this is route 1. Let's just do route 1, route 2. So these two routes intersect because after the 3 on your when t is equal to 3, say, or 2, depending on if you start 0 or 1. Let's say at the third time increment, they both stop at 7, and that's how you can make it stop, right? Actually, maybe maybe I misread this. This is really sorry. Uh, Let me play around with something because maybe I just misread this, to be honest. For example, if or maybe I'm sorry. You're right. I think it forces me to think about it a little bit. I think this. I think I just made this way more complicated than it needed to be honest. Because I think initially that I thought that they have to be at the same stop at the same time to make that transfer. But looking at the problem again, that actually may not be the case. So if that's the case, then I mean, so yeah, so you're right. So like, yeah, so they don't need to be at the same stop at the same time. It doesn't seem like. So this actually makes it a lot easier. So yeah, so you would do some. So rolling back a little bit. So yeah, you would definitely do some kind of shortest path. Maybe is BFS, and in this case, it makes sense because if you do bus transfers, then yeah, yeah, exactly. So my initial kind of going back a little bit was that two routes intersect each other if they kind of have the same state. If they had the same stations at the same time, which that's what I thought was kind of the problem. And to be frank, even if that's the problem, eventually, if they have the same number, they'll loop. So, but yeah, so first you would construct all the graphs. You'd construct a graph where R1 intersects R2, which means that they share at least one bus stop, as if you're talking to, and then we just kind of do something on BFS. Yeah, so I think that's mostly right. So I think we just need to do kind of how do we want to do it? So yeah, so we'll probably just construct a set for each of these routes. Yeah, and then that would allow us to kind of iterate things and check for things really quickly. Okay, cool. Let me just do that pre-processing now. Okay. Maybe I don't even need to do that. Oops. Maybe something like that. Yeah, maybe yours is way cleaner, but so maybe something like that. Okay. No, I mean, I need more practice with Python. I mean, I've been doing Python for a while, but I've been doing more Go lately, so I'm still just playing around. But definitely let me know if I could do things more Python. I'm always here to learn. And you know, okay. So that hopefully sets it. Okay. So now we construct a graph, which yeah, I think n squared is not that bad for 500. So it's v squared even if you want to put it that way. So for yeah. Oh, wait. Well, actually, now this would sorry. Well, may I jump ahead a little bit too much? Because if we do the naive intersection, then actually, I think I did this the wrong way. Because what I was heading toward doing was like for each stop on the station, check to see if it's in another station, right? But actually, I think we could pre-process this a little bit smarter. Instead of doing this, we should pre-process the stops. And let me show you what I mean. What can stop be? Yeah, after a million should be okay. Yeah, okay, fine. Now I have to get the biggest number first, so okay, fine. I guess we could just use set, actually. I mean, not set, but a map. Where's index? How do I also get the index? I always forget. Okay, fine. Got some homework on cleaning this up, but oh, there you go. That's the one. All right, I'm going to keep this for now, though. What am I doing? So for each stop. Okay. I have to initialize this to steps. Okay. So now we can construct the adjacency list, maybe even matrix. Yeah, if I want the list. Okay, fine. And we, okay, this is stops. Okay, fine. Whoops, I don't know what I'm doing. Copy and paste in my head, except for I type it out. So now for each stop that shares the same, for each number in it, we, yeah, there's an edge between all pairwise stop numbers that are in the stop. Okay. There's probably a more Pythonic way to do this. I forget how to do the pairwise one. I mean, it's probably in what you would call it, in the counting one, but what, uh, no. Oops. Oops. You're just adding these edges, and also I need to. We need to. Oh, is it? Oh, okay. Damn, I always forget which one is which. But oh, yeah, yeah. Sorry. Yeah, you. I mean, you're definitely right. I meant to do. I mean, I was going to do it this way, but then I brain farted. Yeah. Okay. Thanks, AB Hacker. I mean, I would have been kind of struggling around it for a little bit, but okay. So this should create the adjacency list just for kind of seeing what I did. Let's run a quick print and then run it real quick. Oh, also, yeah, you're right. No, yeah, this is still wrong. But oh, anyway, what am I thinking of? But man, I do not remember Python syntaxes. But no, this is right. Okay. That's very clean. I will change that later. But hmm. Oh man, yeah, of course. I'm sorry, I'm just being dumb. When you mix too many languages in your head, that's what happens. But of course, it's a dictionary. Okay. Mm-hmm. Um, Man, I do not remember 5-1. You know. Is that right? No. Wait, what? Oops. Wait. That's not right. How am I commenting things out? Oh. Full stops and... Oh. Wait. Oh. Okay, I'm just being stupid. Kind of mixed the variables in my head a little bit. Where is this? Oh, now this is a variable. So, okay. So the stop number and the stop set. What am I doing? This looks okay. I have them backwards. I always have them backwards. What? Oh, items. Thanks. Yeah, it's been a... Gonna blame it on the late night here in Sophia. It's 11 o'clock. I had a really long hike today. Okay, cool. Excuses aside, yeah, thanks for man, and that's why I'm practicing. Okay, so this creates the adjacency list that is actually not quite right. Wait, is it? Oh, I mean it's correct, but actually this probably should be a set. So. Yep, of course. Okay, so now the graph is constructed, but yeah, thanks for the heads up. Okay, so now the graph is constructed, and this actually becomes a very standard PFS. I think the confusing part that I had initially was also that I'm not 100% sure why this is so hard, but yeah, now that you have the graph that you want constructed, I mean, and I say this, but of course I've been taking a long time, so maybe that is relatively okay. But okay, yeah. So now we could do some kind of BFS, and now we have an S and a T. Yeah, I mean we could actually do BFS, DFS. I think it doesn't really matter. Well, actually, it does matter. But yeah, I think as long as we do a shortest path thing, it should be okay. And now we have a V plus E algorithm, and it's kind of if you tune in earlier, it's kind of weird because I'm literally like doing the same thing from before, from like the last problem. So I mean, I'm going to try not to copy and paste, but it is essentially a copy and paste in my head. So oops, start with S. Oops. How do I want to do this? Okay. Yeah, let's do a tuple instead. And remind me to complain about this later. If I don't need to, but yeah, okay, fine. Oh, yeah, how do I want to implement it? Okay, fine. Yeah, let's not do it this way then. And this is only 500, so or up to 500. So what's the number of routes? Okay. It's one, then we queue it. And set the distance to okay. I think that's roughly right. Now I'm going to try to do some testing, and obviously I have some mistakes. Ooh. Oh, is this one based? Oh, I didn't. Oh, this is not routes related. It's just the station. So okay. Oh, so that just add a wrinkle a little bit. But we have all the man. But that also tells you that I should read the problem more carefully next time, of course. But because now effectively what we need is actually yeah, actually it's not that bad because we already have the code written. But because so what we have written is assuming that given given a route of S, how do we get to a route of T, which is the answer we're answering, which is not correct, of course. What we actually want is how to get from stop S to ST. But that because of the pre-processing we did earlier, we can actually do this pretty simply, thankfully. So what we actually want, I mean, now instead of a single source shortest path on your BFS, now we want a multi-source shortest path. Multi-source shortest path on your BFS, and essentially what that requires is kind of what I'm doing now and typing it out, which is we instead of pushing just the starting element on the queue, we put other elements on the queue as well on the stop. So, and because we already know, we already pre-processed it here, we can actually get to it pretty simply. So we have for, where is it? Oh, for stop in stop set and stop as wait. This is already a stop set. Okay, so Okay, so that should be okay. Oops, oops, a lot of whoops. And now, instead of getting the distance of just t, we kind of do the inverse. Yeah, the inverse of converse. Yeah, well, the opposite, the opposite of what you're doing before, which is convert all the t's to yeah, the shortest distance. So shortest distance is equal to, say, well, as we said before, the max you can have per distance is 500. So we'll just do, say, 1,000. Doesn't really matter. But for stop and stops t q dot. Oh man, I'm just copying and pasting too hard. This is only the case if, of course, okay. And in theory, both these functions, maybe I would have abstracted to, yeah, I mean, I think that's just because I started these at 0, but so it should be okay. But yeah, and okay. I mean, well, okay, let me submit it before I make a fool out of myself. Yeah, maybe also maybe I should test a little bit more, but I don't know, you could add just some mumbo jumbo, really. Okay, let's see if that's still okay. Oh man, oh, well, okay, that's just a typo on the input. Scared me there for a second. Okay, well, let's just do compiled. Oh, well, so there is a bug. Oh wait, how do I return -1? Okay, so that is still a bug because we set the distance to -1. So when we do the min, you know, that's not clutch. But so this will correctly give us a quote unquote correctly give us a doubt. So yeah, so that's also one thing when you debug in general. Make sure that you could fool yourself sometimes by getting things correct while in a really weird and like unexpected way, which I actually accidentally demonstrated. And in this case, as I was going to say, because the Sentinel value we used was -1, it actually became the shortest distance, but which would have been okay if we didn't have to do this conversion. But now, because we have to do this conversion, we have to do if short 1,000, we turn -1, and I think if I were to rewrite it, then I would actually set this to like some constant up top, which I've known to do, but today maybe I'm a little off today. But because we used it like 4 times, so that's where all the accidents happen. But well, that's actually one if I make a 4 or something again. But well, yeah. Okay. Okay, let's submit. Oh no. Oh, expected 0. Oh, okay. I was worried about some edge case, and I guess this is an edge case where, well, your start and stop is the same. So I don't know. These things are always a little tricky sometimes for me to kind of like know how I feel about it, because on one hand, like by the letter of the problem, usually it's true. Like, yeah, these edge cases, but I think like it depends on who your interviewer is and what they're testing for. Like, yeah, I did not consider the case where the start and the stop is the same stop. So start and the start and the terminal is the same stop. But yeah, so we did get it correctly. Minus an edge case, which I'm okay with. Yeah, so a couple of things. First, as an interviewee, definitely first thing I would do is improving the code. Alright, how do I minimize this a little bit? Definitely, this has to go. This should be like, even if you have a cheesy like max equals 1,000, and then just move it here. I mean, because that's just a terrible code smell, and I would apologize profusely and just do it as soon as I kind of get it working, maybe even halfway through, because that's pretty bad. The second is what may be kind of it's just 57 lines of code is actually a little bit longer, even as I try to keep it kind of in one function, kind of depending on the volume, obviously. I would probably kind of modularize this a little bit, or large even, special. Yeah, just to kind of make things easier to understand. I think otherwise it's okay. I think maybe I could have explained this better, the pre-processing. So basically, this is just kind of allow us to do the intersection of all the routes at the same time. And the complexity you can see is that this is V plus E in that, is it really V plus E? It's this one's in the total number of elements in in routes. So you have 1,000. Well, I guess it could only go up to 500, but 500 routes of 500 elements each. Then it does that, right? So it's So which is so it is linear in the term in is linear in the size of the input size, but which is so and everything else here is roughly true. I think this is the only thing that is a little sketch, maybe. And what's the running time of that? Well, this is adverse n square. If you have a route square, let's say n is the number of routes, because because you have to create the list, and if it's a full graph, then you have v square and that's. If you have to construct the graph, that's the way you have to do it, right? Like if there's an edge to every other edge, then there's always going to be, and then it's just going to be v square, which I guess thankfully they didn't do anything crazy, which is because it may actually even be a little, because this could be in theory 500, and for each of these it could be 500. So I don't know. That's actually a little surprising. I guess they don't have a stress test on this one, but 500 cube is a little fast, but a little slow. But everything else is just like for this is as you point out, it's a multi-source shortest path, but essentially it's still a path first search or BFS. So it runs in linear time, V plus E, especially since we created the adjacency list. Can we do faster than that? So I think that. Yeah, so that's how I would kind of explain the complexity. I mean, maybe I hand-waved it a little bit, and I would go into more of the interviewer. As an interviewer, I think that essentially it's still a breadth first search problem. I think I like the level of difficulty. A breadth first search is kind of fundamental, even though it's a little graphy in this part. I think it's a little bit on the trickier to understand side. Especially on the stuff about like sequence 157. I don't know. So I think the wording could be a little bit misunderstood and stuff like that, which I have. So maybe that's my little bias over there. But I think in terms of like after you get that, the difficulty is probably a little bit on the roughly. I think it's a good representation of a good difficulty. I think it asks you to do some pre-processing, which you then have to analyze a little bit, and before doing the kind of easy to write, or not easy to write, but standard-ish you practiced the BFS, and so I think I would consider putting this in an interview. I might have to calibrate a little bit and make certain parts, like maybe reword it if I get feedback that is a little kind of confusing to all. But BFS should be in everyone's arsenal, so I think this should be okay.